This is Nanoscape. I'm Seth Zimmerman.
And I'm Erin Spain.
On this show, we venture into the frontier of nanotechnology
With experts in the field who are turning the science of small into the next industrial revolution.
This podcast is brought to you by the International Institute for Nanotechnology at Northwestern University. Today's guest, Robert Macfarlane, is one of the world's pioneers in what you might call molecular craftsmanship. His lab builds programmable materials, which are structures that assemble themselves. They respond to their environment and behave with kind of logic baked right into their design. And it's redefining what it means to design materials one molecule at a time.
So let's find out more about how matter becomes programmable and the next industrial revolution that could happen literally molecule by molecule. Welcome to the show, Robert.
Thanks for having me.
We're so happy to have you here. You are actually a Northwestern alum. You trained in the Merkin Group here at Northwestern.
Yeah, about a decade ago, yeah.
Now you're at MIT leading your own research program that's focused on what we were talking about, programmable matter. Tell us a little bit about this academic journey of yours and how you think your trajectory shaped your view of what's possible.
I started out my academic career as a chemist. My degrees are all in chemistry, both the bachelor's, the master's, and the PhD. I'm now in a materials science department. The transition from chemist to material scientist started at Northwestern with working in Chad Merkin's group, understanding that chemistry focuses on the molecules and what exactly is happening between atoms to, synthesize different structures. But once you start putting enough of them together, you get a material, and understanding what happens at length scales beyond just the molecule is what our focus is now. So we use our chemical understanding to influence the way we synthesize and build different types of materials.
What was it about the Merkin Group and that experience that really changed basically what your plans were for the future and how you're doing science?
When I started my PhD at Northwestern, I wanted to be an analytical chemist. I didn't entirely know that analytical chemistry was going to entail. I knew that I liked a lot of instrumentation and I liked a lot of taking measurements. Then when I was looking for a research group to join, I just sort of by chance happened to attend a seminar given by one of Chad's students and realized that actually was a really exciting opportunity to do nanotechnology and sensor development. So I joined Chad's group initially wanting to work on some of these, DNA-directed nanoparticles for sensors and biomedical applications. But when I joined, he said, no, you're going to work in the self-assembly thing, which turned out to be a very life-changing in a positive way because I found out I actually really enjoyed and was excited by that work. So it was completely random chance that I sort of fell backwards into this, but that's really set me off on the directions that we're going in now.
How would you describe your lab today?
Our lab is an interdisciplinary lab that sits between chemistry, material science, and engineering. And the tagline that I sometimes use when I'm talking to people in industry is that we make the materials that make new technologies possible. That's kind of what we're trying to do. Rather than sort of saying well, these are the materials I can go to the warehouse and pull up. What if we could make new materials that removes restrictions and boundaries on the types of technologies you can create? And so really what we're trying to do is understand, starting with the molecular and nano level, what types of materials can we build? Then understanding once we've got those structures, what properties do those structures induce? And then from there, what exactly can those properties enable these materials to be used for? So really, we're a materials discovery lab. I often don't really know what discipline I'm supposed to be in because I'm not really a chemist anymore. I'm not really a material scientist, not really a polymer scientist. We're a little bit of everything. But I think that that's what's exciting about this is understanding how those different disciplines come together and enable you to make things that would have been a pipe dream 50 years ago.
Your materials often have a pattern or a symmetry. There's an aesthetic to them. Do you see kind of any sort of artistic dimension to what you're building?
I was actually an art minor in undergrad, and so that may be partially what drew me to this. I mean, a lot of what we started building was crystals, and crystals make very interesting shapes. They're sort of these repeated geometric patterns. Shape and the way shape influences material structure is sort of a theme of everything that I've done since joining Chad Merkin's lab and going on into my independent career. And so I don't know that there's a direct connection to art, but definitely it tickles the same part of the brain that made me want to be an art minor.
You are not the first person with an artistic background who we've had on this show. It's kind of amazing. Some people are like, actually, I'm just waiting for the next phase of my life to get back into the art studio and start making art again.
Exactly what I was saying. It was like, how many of them I had to make this choice. It gives me hope that my scientific career is still going to blossom at some point.
Sure.
Yeah.
The phrase, the Industrial Revolution is happening molecule by molecule. Do you agree with that? And what does that mean to you?
I think it's an interesting turn of phrase. Like I said, I started out as a chemist where you think about atoms and molecules and the bonds between them. And now I'm in a material science community where you think about structure across multiple different length scales. So the phrase that I think we're almost obligated to say in every one of the classes we teach in MatSci is structure dictates properties. And so if you know the structure of material, you know what properties it's going to have. So saying that the Industrial Revolution, molecule by molecule, well, molecules become the materials. Materials have certain functions and properties, and that enables new technologies and new directions for society and the way this science can go. So it all starts with the molecules and the atoms themselves, and starting with how they bond to each other is really what drives everything else.
Why is DNA and molecules, why are they so powerful as a programmable construction system for materials?
DNA as a building material is actually quite interesting. So, DNA is the molecule that tells us who we are. It allows, the blueprint for life and all of that. But using it as a building material, it's sort of in this very nice sweet spot where it's incredibly programmable because it's basically a long string that has a bunch of nucleotides hanging off it in a specific sequence. Those nucleotides come in pairs, adenine pairs with thymine, cytosine pairs with guanine, meaning that if I have two strands that have complementary sequences, they'll bind to each other. And it's in this sweet spot where that's enough complexity that you can make a huge range of different things, but it's also simple enough that we can predict, understand, and program it. So other sorts of things that we used in biology, things like polysaccharides or proteins, they have way more complexity, which means that they potentially could do more if you could really program them, but they're not nearly as easy to understand as DNA is.
So DNA was this first programmable system, but then at MIT, you merged DNA guided assembly with polymer self assembly. Tell me about this evolution.
When I was at Northwestern, I joined the group at a time when they had been working with DNA grafted nanoparticles for a decade and a half at that point. It started in 1996. I joined in 2007. And they had just figured out how to take this DNA grafted nanoparticle and make actual ordered structures out of it. The things they had done before were mostly focusing on an individual DNA grafted particle or assemblies that were random and had no real structure. And when I joined, Chad basically said, okay, you've got a couple of different options. You can take this in a couple different directions, but the topic is wide open to you. There's a whole bunch of things we don't understand. We've just opened this new area, and I want you to figure out how far it can go. I didn't actually work with polymers to start. I was just working with nanoparticles and DNA strands. The reason I got into polymers was about the time I was a third or fourth year grad student, and I was presenting this research at conferences or talking with people. I kept getting the question, do you need DNA? Does it have to be DNA? And I couldn't help but start thinking about it. Does it need to be DNA? DNA is certainly fantastic, and it's the most programmable tool we have in our nanotechnology kit, but it comes with limitations. And so some of those limitations are the scale. You can't really make kilograms of DNA. It comes with limitations that it only works in specific environments. So it was basically evolved to work in salt water. So the typical environment you'd find it in a cell. It is a material that has a single structure and therefore a single set of properties. And so the question sort of became, can we use the concept of DNA programmed assembly of nanomaterials, but replace the DNA with something that is a little bit more versatile, is a little bit more scalable, is a little bit more unique in terms of being able to make materials with different functions. And so after Northwestern, I specifically went to work for a professor named Bob Grubbs. He's at Caltech. He was the Nobel Prize winner for his work in basically a specific type of chemical reaction. But I learned in his lab how to synthesize polymers and how polymer scientists think about different sorts of materials. And the end result of merging those two was basically you could look at the DNA functionalized nanoparticle that was developed in the Merkin lab as sort of a template of needs to have properties A, B, C, and D in order to make it into a programmable matter. And so I merged the understanding of polymers and supermolecular chemistry I gained at Caltech with the understanding I gained of self-assembly with Chad's lab at Northwestern and came up with a new building block that can do a lot of the same things, but can do it in different ways and allows us to ask different questions.
I mean, that really kind of blew up this whole new area of research. Is that right?
That's right. So we've developed this building block. We call them nanocomposite tectons, or NCTs, because one of the things I learned from Chad is a good acronym is important. And so three-letter acronyms are always better. But the idea is a nanocomposite tecton. It's kind of like the DNA functionalized nanoparticle, but it uses synthetic polymers, which are much easier to synthesize and scale up. And the major thing it's allowed us to do is to look at what happens when you have larger quantities of material. So the research is not about just making more. It's about what questions can you ask and answer when you actually have more material. So we're thinking about things like processing. How do you not just make a crystal out of this, but how do you then process into a specific physical format that has a specific shape or function? We talk about things like microstructure, which is when you have these crystals, it's not just the same repeated pattern over and over again, but there are defects in it. And using those defects can allow you to program other types of properties as well. So these are things that material scientists have been working with in atoms for decades, but nanoparticles and nanoparticle assemblies are just now being able to look at them because we now have materials that we can think about doing at scale.
Your lab, it controls structures that are across molecular and nano, micro, and macro scales. So how do you design materials that stay organized and coherent across so many different length of scales?
Yeah, so that's one of the major challenges that I was alluding to, that these sort of questions we can ask and answer. So whatever molecule we use to control the particle interactions, whether it's a supramolecular modified polymer, whether it's DNA, which we still do because DNA is too great to ignore as a nanotechnology tool, that basically gives us local control. It allows us to dictate which particles form bonds with one another. And so essentially, if you think about it from, if I can anthropomorphize a little bit, what each particle is trying to do is maximize how many bonds it can make to different particles around it. If it has, dangling DNA strands or polymers that can form bonds but aren't bonded to anything, it's going to keep reaching out and trying to find something to connect to. So the molecular level allows you to control structure right around each individual nanoparticle. And so this is why a lot of the things that we've made are these crystal structures, which are a repeating pattern over and over again, as each particle is basically finding the same ideal environment as all of the other particles in the solution that are identical to it. So you get this, repeating pattern over and over again. In order to control structure at larger length scales, you have to be able to put more information into the system than just the molecular bonding. So one of the ways we've done that is we paired it with lithography, the idea of coming in with, something like an electron beam or a photon beam and basically patterning a surface and then growing the assemblies upwards from the surface. So that allows us to dictate on a specific surface. We can pattern on specific shapes that can act as landing pads so the particles self-assemble upwards from the surface. But we also can look at things like processing, which is, I generally refer to it as, it's the synthesis after the synthesis. So you make the material and then you have to process it into the appropriate form, meaning that you're going to do other things to pack it into larger forms. You're going to mold it, you're going to shape it. And that's really how we are able to control larger scale structures. These crystals, when they start to come together, the particles really don't think any far beyond just the local environment. But if we start packing them into large arrays, you start to organize the overall structure as well.
So these nanocomposites now that your team is building and studying, what are some of the most promising real-world applications that our listeners might be interested in?
These materials we're building started out basically with that question I mentioned earlier that, do you have to use DNA? Can you invent something else? So we invented the NCT, and it does not everything that DNA can do, but it does a lot of it and allows us to ask a lot of new questions. But the major thing that came out of that was we had to solve a lot of chemical challenges to synthesize and make these things. And it forced us to start thinking about these materials slightly differently. And so as one of the things I learned at Northwestern as a PhD student is a good project is one that allows you to go in a million different directions and allows you to discover things that you never intended to. And so a lot of the interesting stuff we're doing now, if you asked me about it 10 years ago, they wouldn't even been a blip on the radar. So some of the things that we're thinking about, one of the areas that I think we just published on earlier this year, it doesn't involve self-assembly, but it involves polymer grafted nanoparticles, where instead of using bonds that allow us to organize them to ordered arrays, allow us to make very strong bonds between the particles. And this allows us to make a material where we can process it like a polymer, meaning you can heat it just a little bit above room temperature, press it into a mold, shape it, whatever. But then we can cross-link the polymers together and make it significantly more stable and rigid. So it's kind of like taking something with the mechanical properties of toothpaste, putting it into a mold, and then shining a little bit of light on it, and now it has the properties of a rigid polymer. So what that allows us to do is make materials that can be used for different applications like flexible electronics. One of the things we showed in the paper was we made basically custom-fit biomedical devices. I say biomedical devices. It was just a thing that went around my student's finger and had a light on it. But the idea was a lot of electronics, things like, an LED or a sensor component involve rigid materials.
Yeah.
And if you want to make a flexible structure, you have to find a way to integrate that with a flexible component. If I just took an LED, for example, and glued it onto, something like rubber or soft plastic, I could bend the rubber, but as soon as I bent it, it would break the connection to the LED. It would, snap off of the rubber because the LED couldn't bend with it. So what this technology that started with NCTs and now is into this new three-letter acronym, a cross-linkable nanoparticle, an XNP, what allowed us to do is basically take a material that is initially flexible. We can shine light in specific regions to make those specific regions rigid, and now we can put electronics or components like that on the device itself. So the majority of the device can bend and flex and operate in different shapes, but the part that actually needs to remain rigid stays rigid, and it's one continuous structure. So one of the examples we showed was you can basically take a sheet of this material before it's cross-linked. We wrapped it around the student's finger, sort of drew on there where exactly we wanted to cut it and where we wanted to draw the circuits in. You can then take it off her finger appropriately, hit it in certain regions with light to cross-link it, cut it out, and then have a custom-fit biomedical device so that we didn't have to, take any measurements of anybody's hands or fingers to actually make. So there's potential for this in flexible electronics, biomedical devices, all sorts of different stuff.
You have talked about being flexible in your lab and having to kind of go with the flow as you're discovering things. So is there anything a moment in your lab recently where the structure or material just kind of behaved in a completely different way than you were expecting?
The most interesting things we've been doing typically happen that way. We set it to do one thing, it doesn't work, but it works in a weird way, and so we pursue that in some sort of new scenario, new project, new different avenue of discovery. So there's one that we're going to be publishing it soon. It's not out yet, and so we filed a patent on it, but we have not actually published it yet. We had a high school student working with us a couple of summers ago. He's now a first year freshman at MIT, because he's super brilliant. But when you have a high school in the lab, you have to be very careful about what science you do. They're not allowed to do anything completely dangerous, and so we had to hunt around trying to figure out a project for him. And so the project that the postdoc who was working with him came up with was trying to make something that's called a Pickering emulsion. Basically, an emulsion is when you have one liquid droplet inside another liquid. So like vinaigrettes or emulsions, so the oil suspended in water. What a Pickering emulsion is you make that emulsion and then you add in nanoparticles that sit at the interface between the oil and the water to help stabilize it. And so they figured that would be pretty easy for the high school student. He's just working with water and maybe some organic solvent, some particles. He's just shaking them up and like mixing salad dressing. It wouldn't be that hard. But what ended up happening was instead of making basically an oil droplet that had a bunch of these particle spheres on its outside, we got oil droplets that had a single particle per oil droplet, and all of the oil droplets were exactly the same size, which doesn't normally happen. But being able to make these sort of particles that are all exactly the same size, that's step one of being able to make any sort of assembly. So the analogy I like to use is like if you go to the store and you see all the oranges stacked up and you see all the grapefruit stacked up and you try and put an orange in the grapefruit pile or grapefruit in the orange pile, everything gets messed up. You want everything to be roughly the same size and shape. And so these particles that we accidentally made, not only were they really low dispersity, they had all the same size, same shape, we could tune that shape all the way from 50 nanometers up to 5,000 nanometers with pretty good precision. And that allowed us to work in a regime that there aren't a lot of good particles for, which is about 200 nanometers. So we have a lot of examples of nanoparticle syntheses that are great at like the 10 nanometer or 20 nanometer regime. There's a lot of syntheses that are great at like the 1,000 or 2,000 nanometer regime. But for various reasons, that 200 nanometer regime, there aren't a lot of good syntheses. But that's exactly where you'd want to be for a lot of interesting optical materials, because that's comparable to the wavelengths of visible light. And so what happens is you take these materials that we've synthesized accidentally. If we spin them down in the centrifuge tube, so basically you pellet them all at the bottom, they pack into an ordered lattice that becomes a vibrant color based on the size of the particles. So these particles themselves are completely transparent. They're invisible to the human eye, but when you spin them down and put them into an ordered lattice, they become bright blue, bright green, bright red, depending on what their size is. And so this allows us to make materials called photonic crystals, which are potentially useful for all sorts of different applications. And so we're currently in the process of exploring what we can do with that. We've incorporated a company to actually start making technology and devices out of this. And self-assembled particles and photonic crystals has also existed for decades. But the major challenge is being able to scale it up, process it, and make something functional out of it has always been really challenging. And these materials allow us a lot of new opportunities to do that.
Could you give us some examples? Like, what could we be talking about
Yeah.
here?
Are we able to talk about this too? Or is it too secret? You don't want it out there yet?
So we're going to be submitting the paper soon. We've already filed the patent on the technology, so there's some things that I can't quite talk about just yet, but I can give you some basic ideas of what you could do with them. So this is actually the major challenge. The postdoc was the one who decided to do a startup company based on this because we knew that we had something special here. We just didn't quite know what it would be good for. There are a whole bunch of things that it could be used for, but finding the ideal application is sometimes tricky. So if you didn't set out to make a technology or device, but you have a material that has a bunch of interesting properties, you got to hunt around and figure out, okay, what is the best best thing for a startup to pursue. So some of the things you can do with photonic crystals, you can make very complex optical devices for optical circuitry. So this is a thing that people have been talking about for a while. Instead of using electronic circuits, you use photonic circuits. So instead of pushing electrons back and forth, you're pushing basically photons, packets of light back and forth, which allows to do things like compute faster, compute with less energy. And so this has been a big thing for like the AI revolution of trying
Yes.
to figure out how to make these types of optical circuits. One of the major components you need is you need photonic crystals in certain regions to be able to direct light and photons where you want it. And so one of the applications we thought about was using these to, instead of use lithography to come in and have to write each sort of photonic crystal individually, just pattern a surface once and then have the photonic crystal grow upwards from there in the site you need it. The other areas we've thought about are photonic crystals are this really bright, vibrant color. So if you see anything in nature that looks shiny, it's because of a photonic crystal. So beetle shells, butterfly wings, that kind of stuff. Because they have these really nice, vibrant colors, and because they self-assemble so readily, one of the applications we thought about was just simple paint. So something you can spray onto a surface that isn't going to photo bleach or, decay out in the sun. Is just going to be this really nice, vibrant red, blue, green, whatever kind of color. Ultimately, the technology that we're targeting is actually heads-up displays for cars or other types of
Cool.
vehicles. The idea being that you're driving down the road, you're looking through your windshield, and then you're seeing things on the windshield like, here's your speedometer, but also here's a car to your left that, might be coming into your lane, or here's directions on the exit you should take. So the way that would be working is you basically put a film of these things over your windshield such that it only allows certain wavelengths of light to be reflected, meaning that most of the light can come through your windshield, you can still see the road, but you've got a little projector sitting behind you that is going to project an image onto the windshield itself, and that specific wavelength of light, that specific color is going to be reflected back into your eyes. And so that's how you overlay the heads-up display onto a windshield.
And let's talk about this high school student. My goodness, this is one of those stories that's just like this happy accident in a lab by a teenager. It could now be part of like a major, industrial revolution, as we were saying. Like, this is pretty incredible.
Yeah, so the high schooler himself was pretty fantastic. And like I said, he's now a freshman at MIT because he is brilliant and he's still working with us. He still comes into lab. He's a little bit busier now that he has classes. One of the things that I find is really important about science is having good people and having good people that are willing to work together, talk to each other, discover things. So the idea behind this, the high school student did do the project, but he was working with the postdoc. And so it was the two of them together that kind of found this sort of weird thing. And my guess, I wasn't in the lab when this happened, my guess is that the postdoc was explaining to the high schooler, here's what we're going to do, here's what's going to happen, here's what's going to look like. And then they pulled them out of the centrifuge and there was this weird color they didn't expect. And so that's what sort of led him down this interesting route of trying to figure out what's going on here. Most of the stuff that we do involves weird things happening that we don't understand or can't explain. But then the students or postdocs or people in the lab can go to each other and say, I have this weird result. What's going on here? That's, I think, one of the most important and best ways to actually make scientific discoveries is to be open to the possibility of something weird happening and then have good people that can help you explain what exactly it is.
Do you think of yourself as sort of a designer or a craftsman of some type? Or is that something that you don't really see that you're doing?
I definitely do, but I think about it in a different way. Science is a creative discipline. You typically think about artists or writers, but science is an incredibly creative process. And so there's a lot of design that goes into it. I think people understand that a little bit better if I said, what if instead of saying a scientist, I said an inventor? Everybody would agree an inventor is a creative person, but that's really what we are as scientists and engineers. We are inventing new products, new materials, new knowledge. We're trying to ask questions about things that nobody understood before. And there's a lot of creation that goes into that. So I do think of myself as a designer in the sense that we're trying to make new things. And that involves some aspect of designing the building blocks that are going to be going into that.
Every field has, let's say, a blind spot. So what is the blind spot in nanoscience and nanomaterials that you think we're going to look back on and just say like, oh my God, how did we not see that sooner?
So what I would say is it's not really a blind spot right now, but it was maybe 5 to 10 years ago. And this is a little bit of a self-serving answer because it's what we focus on, but it's the idea of processing and scale up. The idea if we want to make a material that is actually functional and useful, it's not enough to just make a little bit of it. You have to make enough of it that you can start to put it into different functions, shapes, or forms. So that's not necessarily a blind spot because nanotechnology has been having an impact in many fields and many disciplines for decades. Take, for example, the stuff going on at Northwestern with these spherical nucleic acids that are used for biology and biomedicine. They weren't used as like large macroscopic sorts of materials, so you didn't really have to think of processing or microstructure or macroscopic perfect form. So I think that's the blind spot that we're now sort of coming out of, is it's not enough to just make the material. You have to make it and put it into a functional form. So understanding how to move beyond just the nanoscale, that's the blind spot that we're now starting to address. And it's because we've been able to spend the past 2 decades really understanding the chemistry of nanotechnology. So I wouldn't necessarily call it a blind spot now, but definitely it's a blind spot that we're now becoming aware of.
Thank you so much, Rob, for coming on the podcast, talking to us about the work you're doing and how it could really change industry in the future.
Yeah, thanks.
Thanks so much for listening. This podcast is brought to you by the International Institute for Nanotechnology at Northwestern University. Be sure to follow this show on Apple Podcasts or wherever you listen to podcasts, and be sure to give us a 5-star review.
For more information about IIN, go to our website, iinano.org/podcast.